Hello and welcome to the third part on the Measure of Intelligence by François Chollet. Now, this is a multi-part series. If you haven't seen the first two parts, I recommend to watch at least one of them. They're somewhat overlapping, but we've basically gone over the history of intelligence measurement and the foundations of what a measurement for intelligence for an AI system should look like. And today we're going to get into the formal definition of the intelligence that Chollet proposes right here. So this sentence here pretty much sums up what we're interested in. The intelligence of a system is a measure of its skill acquisition efficiency over a scope of tasks with respect to priors, experience, and generalization difficulty. So these are the things that we've established so far, basically. The intelligence of a system, that's the thing we want to measure, right, is a measure of its skill acquisition efficiency. So how fast does it acquire new skills? Important here is that we are measuring it over a scope of tasks. So it's not arbitrary skills, it is a scope that we define, and this is going to be mostly the human scope, the tasks, the scope of tasks that humans can solve and are sort of different at. And what we need to factor in are priors, which is what is already built into a system, because that doesn't count as intelligence, that's already built in. If your ability to solve a problem is already built into you, you don't have to use intelligence to solve the problem. Second, experience. If you have had lots and lots and lots of experience at the particular task you're asked to solve, you don't have to use intelligence, you can simply rely on your experience. And the third is generalization difficulty, and that's a property of the task. So if the task is very difficult to generalize, so if it's very difficult, if the task itself is very difficult, then achieving a good score at it should count as having higher intelligence if all other things are equal. So this is going to be the basis, and today we're going to watch Chollet define these things basically into a number that can give us the intelligence of any system with respect to these things. Okay, so that's the program for today. If you like content like this, share it out and tell all your friends and leave a like so that YouTube knows that you do like it. Okay, so the conceptualization of the entire system is like this. There is a task, and we're going to consider a series of tasks, of course, but if we just look at one task in our scope, there is the task, and the task outputs these situations. Okay, which in a machine learning term, these are like your training examples, right? And on the other side, there is the intelligent system. Okay, now the intelligent system in a pure machine learning side, you would factor this as the task gives the intelligent system something like a training sample, or in reinforcement learning, it would be something like an observation, and the intelligent system, gives something back like a response. Here we have a kind of a in-between step. The intelligent system doesn't actually give back the response to the situation. The intelligent system generates a skill program. So the intelligent system will generate a program that can map the situation to a response. And that skill program should be able to run on its own. Okay? So in the classic machine learning sense, if we look at supervised learning, for example, the intelligent system would be like a ResNet plus SGD. Okay, that is an intelligent system, and if it is it is able to generate a skill program. Okay, so during training, what happens during training? During training, the intelligent system is able to intervene in the skill program at each step. So the situation comes in, and then the skill program does something, but the intelligent system can, at any point, it can kind of intervene and update the skill program and generate a new skill program for the next step, right? So there's a situation, the skill program gives a response, and the task gives feedback in form of a score. in machine learning terms, this would be your training sample. Your training sample comes in, your neural network gives a response, which are the logits of the classes, right? Then the task gives a score to that, which in the supervised learning case is the label or the loss function as a feedback to the intelligent system. And the intelligent system, using SGD, would update the skill program for the next step. Okay, so at each step, the intelligent system can update the skill program. That's why the intelligent system in this case is the architecture of the neural network and the procedure to update the weights. Not the weights themselves, but the procedure to update the weights. And the skill program here, those would be the actual weights of the neural network, or like the instantiation of the ResNet with these particular weights. Okay. Now at test time, we sever this connection right here. So this is now severed at test time. At some point, the training is done. The task says, okay, now training is done. And then the intelligent system will produce one last skill program. And then this connection is cut. And the skill program must by itself answer to these situations. It cannot, the intelligent system cannot intervene anymore. And in this loop here, situation, response, this goes over for a number of steps, and all the scores during that time are counted and tallied up, and at the end, the higher the score, the better. So the intelligent system must, at this end step, produce a skill program that by itself can achieve a high score. Okay, so there's always this training phase first, and then there is the test phase. Now, the training phase, these situations that we get in a training phase, they are called a curriculum in this world. In our world, this would be something like a training data set. But this is curriculum. It's slightly more intricate. But just the notion here makes sense, right? The intelligent system produces the skill program. Okay. So there's a lot of formalisms right here, like, okay, the task has a situation generator, and that maps the task state to a situation. So the task can have a state, and the skill program can have a state, and the intelligent system can have a state. And I don't, like, this is all a bit too formal. You don't really need to understand it, except if François Chollet is watching this. I think I have found, I'm not sure if it's a mistake, but you say the intelligent system here consists of 3 objects. So it generates the skill program according to its internal state, okay, and it generates the skill program. And when it learns, it updates the internal state according to, let me, if I can find it, right here. A self-update function. So this is how the intelligent system can update itself, so its own state. So it takes the internal state of the intelligent system and outputs another internal state. And this is the, where I said the intelligent system at each training step, it can observe what happens and basically react accordingly. So it takes the situation, the response, and the feedback and its own internal state as an input. Now, what do we have here? It takes the situation, which would be, in our case, the training sample, the response, or the logits that the neural network has produced, the feedback, which is the loss, and its internal state. Okay. Now, what I argue is basically that it should also get the internal state of the skill program as an input right here, because the skill program can have an internal state. All of this, like the response, can be a stochastic procedure of the skill program. And I guess it's not necessary because you can sort of infer it, but I think the framework would be more complete if the internal state of the skill program at that time were part of the intelligent system update procedure. Just, you don't, okay, this is not relevant. This is just me bickering. Cool. Let's actually jump all of this. This is boring. This is very boring. Okay. Blah, 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 blah. Lots of definitions. All right. quantifying generalization difficulty, experience, and priors using algorithmic information theory. So these things that at the beginning we said we want to define intelligence with respect to, we are now going to quantify using algorithmic information theory. Now, algorithmic information theory in this case right here that we're using is not very complicated. The main quantity is this h, the algorithmic complexity. The h of s is the length of the shortest description of the string in a fixed universal language. Okay, so it's the length of the shortest program that outputs the string when running on a fixed universal Turing machine. So basically, if you have this string s right here, s is a bit string, the shortest program that can compute s, or so in the worst case that's the string itself. But if the string is like 0 1 0 1 0 1 0 1 all the way, you can just say 0 1 times 50. And that would be like the shortest program to produce that. It is an information theoretic concept here, but in essence you can just think of it as a measure of how long is the program that I would need to write to output a given to produce a given output. Okay, so that's the algorithmic complexity, and then the second quantity right here is the relative algorithmic complexity, which is almost the same thing. It's how long is the program that I have to write. So the shortest, we're always talking about how long is the shortest program that I have to write that produces S1, but is allowed to take S2 as an input. Okay, so it can never, it can always ignore S2. That's always a possibility. So if S1 is like a super easy string, you can just output that. But if S1, let's say S2, here is 0 1 0 0 1, okay, and S1 is 0 1 0 0 1 0 1 0 0 1, okay, so it's just twice that. So you could sort of output that string here. You could write a program that just outputs this, or you could write a program that just says 2 times S2. Okay, so the length of this is not part of the program. The program is just 2 times S2 because it's allowed to take S2 as an input. Okay, so this is the relative algorithmic complexity is how complex is the program to get from S2 to S1. And so you can almost already see how that will relate now to generalization. Okay, so a few quantities that we need to consider are a task called t here. Then sol t theta is the shortest of all possible solutions of t. So task t has a solution of threshold theta, which the threshold theta is just, this is like the minimum score we need to achieve in a task. We consider tasks according to thresholds, like you need to get a score of 9,000 in Pong or so. So the shortest of all programs that will optimize, that will solve the task to a threshold theta, which is the shortest scale program that achieves at least theta during evaluation. And the other quantity is this train sol opt tc. This has a lot of quantity right here. You can see the task we want to be optimal, but with respect to a curriculum. Okay, the curriculum is the training data. So this quantity is the shortest optimal training time solution given a curriculum. So it's the shortest scale program that achieves optimal training time performance over the situation in the curriculum. So this right here is if we had an oracle that told us here is how to solve the task in general, like the task of determining cats from dogs in images. This would be the program that does it. Okay, overall over the entirety of the task, all cats and dog images there are. That's the solution. Now this quantity right here means sort of the one neural network that is best at determining cats from dogs in this particular training data set, this curriculum C. Okay, so this is the one neural network that is hyper optimized in this particular training data set. And now we assess the generalization difficulty. So the generalization difficulty is going to be a measure of how hard is it to, in a particular task, to generalize to the whole task from the curriculum C. And that's going to be the relative algorithmic complexity to go from this quantity to this quantity. Both quantities we've just explained. So it basically means if I had the perfect solution on the training data set, how much more complex is it to get from that to the perfect solution on the entirety of data? Or you can also guess on the test data set, right? So if this is really easy, so if the training data set already perfectly captures all of the data there is, that this quantity is 0. Like the program, I don't need to write a program. I already have the solution, right? And you can see here we divide by the age of sol t. But however, if the training data has no information whatsoever about the solution to the general task, or if I just so horribly overfit on the training data such that it doesn't help me at all for the general task, then this quantity is 0. So this quantity is in 0, 1 with sorry, the quantity is 1, of course, yes, because the shortest, this thing up here will be equal to just h of sol t, because this doesn't help me in that case, and then this ratio will be 1. So generalization difficulty of 1 basically means that the training data solution doesn't help me at all. This particular training curriculum is useless because I'll just overfit so horribly that I will not learn anything about the task, or I can't learn anything at all. And generalization difficulty of 0, oh, that's, yeah, no. Yes, generalization difficulty of 0 basically means that all of the solution is already contained in the training solution, and I require no work to get to the test set solution. Okay. This is, I mean, I do this train test set. This is all a bit more general as it is written here, but I think it's a good way to think about it. Okay. So the point here he makes is that so yeah, he makes this example right here where he has these two data points where x minus 0.75 has a label false and x 0.15 has a label true, and the shortest possible solution will not help you to generalize to the other things. So the nearest neighbor program would be better prepared for future uncertainty, but would take significantly more space to write down. So there's a trade-off. There's a direct trade-off to how much you optimize on the training data and how much generalization capability you have. Okay, so the next quantity we want to assess is developer-aware generalization difficulty, because so far we've only considered generalization difficulty with respect to the task itself and to the curriculum. But what you could do is you could simply, you producing this intelligent system, you could simply build in the solution to the entire task into your intelligent system. That means it could completely ignore the training data and still perform pretty well on this thing, even though the training data itself, the algorithmic complexity, it tells you nothing about this. So the generalization difficulty would be very high in the measure up here. But so you would think, wow, this intelligent system solves this task really well, but it's because you've baked the solution to the task into the system and it just ignores the training data. So the developer aware generalization difficulty is going to capture that and basically punish you for building the solution, the final solution, directly into the task. So this is the intelligent system right here at time 0. This is basically whatever you pre-build into the intelligent system. It hasn't interacted with the training data yet. This is simply the state at the very beginning. So this is all the priors you build in. If you build a ResNet, it has certain, it has convolutional filters and so on. That's a certain prior on the translational invariance. If you build an AlphaGo system, that certainly has the rules of Go built into the system, and it has this Monte Carlo tree search which biases it towards a certain kind of learning and so on. So all of this is captured in this quantity right here. This basically means that if I am given the optimal training solution as before, and also the initial state of the learning system, how much more work is it to get to the solution of the task? And here you can clearly see if I have already built the solution into this system. So if I'm building a tic-tac-toe learning system, I call it a learning system, but I build in the optimal strategy from the beginning into my system, and it just ignores the training data, then this thing here would be low, because it takes me a lot of work if I only have the training data to get to the solution. But it takes me very little work if I also have the initial state of the system, because the solution would be encoded into the initial state already, right? So any prior you put in there will be captured by this, okay? So otherwise it's the same metric. 0 means it's very easy to generalize to the entire solution. 1 means it's even, it's given the training data solution and the system you give me, that it is very hard for that system. Now consider here, this quantity actually depends on the system you put in. All right? Then we need 2 more things, which are priors and experience. So this was the difficulty. This was how difficult is the task as such, if for a given system and a curriculum. Now what we want to characterize priors and experience. Now priors are pretty easy. What is a prior? A prior we can capture by simply looking at the difference between how complex is the solution minus how complex is the solution if I'm given the initial state. This is almost the same as before, but it now only considers what you built into the system, right? There's no training data anymore. It simply says, if I have, if you give me the source code of your learning system, if I can already read out the solution, then this quantity right here will be 0. There is it's 0 complexity to get from your initial state of the learning system to the solution of the task. And therefore, this entire quantity would be 1. That means the prior, all the information is in the prior. However, if your learning system is a very general learning system, like it's like a standard reinforcement learning algorithm with almost no assumption about the data, then this quantity right here would be very low. Sorry, it would be very high, of course, because the initial system doesn't tell you too much. So it's still a lot of work. If I gave you the source code, it's like, well, this is very general. This doesn't tell me anything about the task. And it would require a lot of work to get to the solution of the task. And therefore, the quantity up here would be very low. And therefore, this would be close to 0. So that means there are no priors in this intelligent system for that given task, okay? And the quantity is always of how to reach the threshold. The solution is always with respect to a threshold in skill. So you must reach like this many points, okay? The important thing that Chollet notes here is that the priors captured not it's not the amount of information in the intelligent system, but the amount of relevant information for that task. Okay, you can make a super duper complex intelligent system. The only thing that matters for this quantity is the amount of information that's relevant to get to the solution of the task T. The last thing we need to capture is experience. Now, experience basically means how much during this learning phase. From now, we just talked about at the outset, like the state at time 0 for the priors. Now, you remember we interact with the task for a number of time in this training phase, right? And the question is, of course, if we are given a longer training phase, it is easier to generalize generally, right? More training data makes our life easier, makes it easier to generalize. And the intelligence is inverse proportional to that. So a system that had, all else being equal, that has less training data but is performing as well on a task as a system that had more training data, that system that had less training data we consider to be a more intelligent system because it can generalize more efficiently. So we need to quantify experience. And experience, now in the same kind of in the same train of thought, is going to be the difference between two quantities. So the first quantity is this. So here we consider at each time step t, okay? So at each time step t, we have the intelligent system, and we have this thing here called data. Now, data is everything that the intelligent system gets at that point in time. So the intelligent system is here at time step t, and then it outputs this skill program, and that skill program gets a situation and gives a response, and this gives a feedback, and all of this data, that's called data. Okay, it's basically, you can think of it as one additional training example, right? You're at time step t, and you're given one additional training example. The experience is going to quantify how much information is in that one additional example. Okay, and then we're going to sum this up over time down here, which basically means over the entire course of training, which is this curriculum C, how much information did you get out of the training data at each step? Okay, that's going to be your experience over the course of training, which again, this is the sum over the experience that you got at each step, and the experience at each step is simply the following two things. So we're going to assess is how difficult is it at time t? So you've learned for t steps, how difficult is it to go from that to the solution, right? So if you might have had some training data, right, and you score like 80% on the test set. So that's basically how difficult it is. It's like you still make 20% of error. That's your difficulty. And then you get one more training sample, this data here. Now you can ask again, if I know everything I'm knowing in my intelligent system, but I also get one more training data point, can I, how easy is it now to arrive at the solution of the task? And now you can say, oh, with this training data point, I now can correct some of my mistakes, and I only make like 18% of error. Okay, so the difference here would be like 2%. So that's going to be, your experience is going to be worth of 2% of errors. Okay, now the important thing here is that it is different if we could have just written here minus h of, sol theta t given the intelligent system at time step t plus 1, right? Because the intelligent system at time step t plus 1 has had that data point at time step t and incorporated it. But that's not the same thing. Here, in this step right here, when we say how difficult is it, we assume that God or Vapnik himself tells us how, like, the optimal way to use that information. Okay, Whereas this thing here, it's not a given that the intelligent system will use that information in the most optimal way. So this is basically the difference between how difficult is it to get from the intelligent system to the solution, and how difficult is it to get from the intelligent system and the data point at time t if you could make optimal use of that data point to the solution. All right, so this is going to be an assessment of how much experience you've had in the sense of, had you been able to incorporate the experience properly at each time step. Okay, because otherwise, you know, you couldn't compare the experience. If two systems had the same experience in the same task, it should mean they had the same, you know, data points in the same order, or in a simplistic sense. All right, so this is all we need. Intelligence, boom, this is it. So there's a lot of stuff here, okay? Intelligence of an intelligent system with respect to a scope. And there are two definitions right here. One is for optimal skill at each task, and one is for threshold of skill. Now we're going to focus on the threshold. As we said, at each task we require something like you must achieve 8,000 points, and we're going to consider the shortest programs that will get to at least 8,000 points. Now there's a bit of confusion in the notation here, as this, I'm pretty sure this quantity right here, you know, should be called something different, because it's, you know, the t is here, and then there's this here, this refers to this, and this shouldn't be out of here. This should be meaning something like thresh. I'm pretty sure this is just a name, like here the name opt. So yeah, in any case, the intelligence is of an intelligent system with respect to a scope of tasks. Okay, and the first thing we do is we're going to average over the tasks in the scope. So we consider all the different tasks, and each task has a weight associated with it. This is the threshold and skill that we want, and this is sort of a mapping. This is a conversion rate, because this might be, you know, 9,000 points at Pong, and another task might be you need to achieve 0.2, and that's really good. A 0.2 is really good. So this W for each task is simply going to map it to like a uniform coordinate space of points of skill level of that particular task. Okay, so but we're going to average over task. Now you can, I guess, disregard this. This is not super. This is just scaling. We're going to average over task. Now in each task, we're going to consider all curriculums that get you to this threshold. So all curriculums that get you to the threshold t for theta t for task t, which means all the possible permutations of training data sets for that task, right? It's more general than this, but we want to assess all the different ones. And as you can see here, there's P of C. So this is an expectation. This is the probability of that particular curriculum. This is the expectation over data right here. This is the expectation over the training data distribution, okay, in the classical machine learning sense. So we're going to take the average across all tasks over the expectation under the training data distribution. So we're good so far. And usually right here, we would put something like the empirical risk, right? The minimum loss, min loss function, min theta loss function over my C, over my training data set, okay? But not in this case, because we now want to consider the priors and the experience and discount that from the difficulty, and that's what's written here. So this is the developer-aware generalization difficulty. This here is the amount of information that's already contained in the priors, and this here is the amount of information that's contained in the experience in that curriculum. As you can see here, the experience is in that curriculum. So basically, a system is more intelligent if the task is harder for that given system and that given curriculum. Okay, so that makes intelligence up. A system is more intelligent if it gets to a certain threshold with lower priors. Okay, if the priors are low, the whole quantity is high. And a system is also more intelligent if it gets to the threshold with less experience. Okay, so if the experience here is lower, it counts as more intelligent. All right. In this quantity, and this is written all in the text here, it has some properties in that it, for example, it downvalues actors that in the same curriculum, like in the same training data, if an actor learns faster, like it learns earlier to reach the threshold, it would assign more intelligence to that actor and so on. It's kind of, sometimes it's hidden over the, it's hidden in the definitions. For example, these curricula are not all the same. The curricula are specifically curricula that you need to reach this certain threshold. So it's not always, doesn't always sum up to 1 with this probability here. That's why it's not exactly an expectation. Let's call it an expectation in quotation marks. But in the general sense, that's it. So the intelligence of a system is over a scope of tasks, the expectation in quotation marks under the training distribution of the generalization difficulty accounted for. We discount the prior knowledge of the system and the experience that the system has had. Okay? And that's it. It says P plus E, priors plus experience, represents the total exposure of the system to information about the problem, including the information it starts with at the beginning of training. Okay, so if this is high, then the system is not very intelligent, or is not. If a system that has more of this but generalizes to the same level as another system is considered less intelligent than that other system because it has had more exposure to information about the problem. It makes a lot of sense, right? So schematically, the contribution of each task is the expectation over skill times generalization divided by priors plus experience. That's kind of in words what we looked at. So it goes over a number of key observations, and at last he goes over consequences, or basically a recommendation for what a benchmark should look like if we regard it in this light. Now, of course, these complexities and so on, they're not exactly computable, right? So like how much exactly the length of the shortest program is not exactly computable, but it can inform our notion of how we should test intelligence. Okay, so what to expect of an ideal intelligence benchmark? First of all, it should describe its scope of application, its own predictiveness with regard to this scope. So that means the validity. It should be replicable. It should be reproducible. It should measure broad abilities and developer-aware generalization. Sorry, it should set out to measure broad abilities and developer-aware generalization. Okay? So that means it should not be solely measuring skill or potential. It should not feature in its evaluation set any tasks that are known in advance, either to the test-taking system itself or to the developers of the system. And that, of course, refers directly to the developer-aware generalization. And it should seek to quantify the generalization difficulty it measures, or at least provide qualitative guidelines with regards to its generalization difficulty. It should at least be made clear whether the benchmark seeks to measure local generalization, broad generalization, or extreme generalization. So we've seen this in part 1. Taking into account generalization difficulty minimizes the possibility that a given benchmark could be hacked by solvers that take undesired shortcuts that bypass broad abilities. Okay, it says it should control for the amount of experience leveraged by test-taking systems during training. It should not be possible to buy performance on the benchmark by sampling unlimited training data. So this already rules out sort of any, let's say, image recognition or NLP benchmarks, because there we can always just feed in more data, the more unlabeled data from the internet, or even labeled data. Like if there's a benchmark that, you know, is on computer vision, I can just pay more humans to label more data, and then I will be better at that benchmark. The benchmark should avoid tasks for which new data can be generated at will. It should be, in effect, a game for which it is not possible to practice in advance of the evaluation session. That's going to be hard, right? It should explicitly and exhaustively describe the set of priors it assumes. Any task is going to involve priors, but in many tasks used for AI evaluation today, priors stay implicit, and the existence of implicit hidden priors may often give an unfair advantage to either humans or machines. So this is, for example, if the test is like a speed test. A lot of times machines are going to be way faster than humans, because the hidden assumption in a speed test is that kind of your nerve conductivity is the same across all test takers. And the last one, it should work for both humans and machines fairly by only assessing the same priors as possessed by humans. And he refers to core knowledge, which we saw in the last part, and only requiring a human-sized amount of practice time or training data. So this means if we want to compare humans and machines, machines can often incorporate way more data than humans. So the tasks in the benchmark should only, like, the amount of data should be such that a human could process that data. Now, of course, that sort of also means that any task where basically you collect data during your life is also sort of ruled out a bit. So that means the AI benchmark task can't be like cook a pan of spaghetti or something like this. Yeah. And in the end, he says, these recommendations for general AI evaluation wouldn't be complete without a concrete effort to implement them. In part 3, we present our initial attempt, which is going to be the ARC dataset and the ARC Kaggle challenge. But that's a story for next time. I hope you enjoyed this and at least got some bits of it. It's very abstract, this measure of intelligence. Of course, it can never be computed exactly, but the fact that someone is trying to formalize, and it's not the first time this has been trying to formalize, but this, I feel it's quite understandable, and it makes sort of sense, and I'm interested to see if people come up with like actual approximations to this quantity that you could actually compute, sort of. All right, that was it. I thank you for watching, and bye-bye. See you next time.